Hello everyone, today my topic is the evolution of high-performance networks, a storage perspective and practices at Alibaba Cloud. Let me introduce myself first. I am a senior staff engineer at Alibaba Cloud. Before the current job, I worked at Microsoft Bing team, focusing on distributed index services. Currently, I have been working on high-performance data center networks, responsible for implementing and deploying two generations of the cloud storage network stacks in Ali Cloud, and our recent work has been published in several top conferences, such as SIGCOMM, ASCA, and ATC. Now look at the comprehensive storage product portfolios on Ali Cloud. The top layer is data-intensive industrial solutions like AIGC, HPC, recommendation, and search. Storage data services are in the middle to meet the needs of different users. It includes simple login services, intelligent media management, and so on. The bottom layer is storage infrastructure services. This layer is internally divided into two sublayers. The infrastructure system is at the bottom, including Pangu, Yuwa, and Kuafu, three core fundamental components for storage, naming service, and network. On top of that is storage services like elastic block storage, also known as EBS, object storage service, also known as OSS, and cloud file system, known as NAS. Pangu is a unified, panel-only persistent distributed file system, which serves nearly all storage products of Ali Cloud, including OSS, NAS, EBS, and DFS. There are three roles in Pangu. Masters are responsible for metadata management, knowing the chunk location of each file. Chunk servers are to read and write data from chunks and ensure the data integrity. Clients are integrated in upper layer services, talk to masters for the file location, and read or write the actual file data through chunk servers. Basically, three copies of each data are saved in different chunks of different machines to prevent data loss caused by disk damage. This means network matters. EBS is the most performance-sensitive storage product and has evolved for 3 generations. With the evolution of storage, the network has also evolved for 3 generations. I will show you how these evolutions happen in the following slides. Let's move on to the first evolution, Gen 1 to Gen 2. For Gen 1, before 2016, Pangu storage system services co-hosted with the storage agent and user VMs. Users' data is often saved in the local machine and another 2 machines in the same cluster. The evolution of the storage network from Gen 1 to Gen 2 is mainly driven by 2 things. First, with the replacement of storage medium from HDD to SSD, both latency and IOPS have increased by about 1,000 times. Randomly reading 4 kilobytes on HDD takes about 6 milliseconds, but for SSD, only 10 microseconds are required. Second, the service architecture has evolved from compute storage hybrid mode to storage disaggregation mode. This is to mitigate unbalanced compute and storage resources and get rid of performance and security problems caused by heavy services on VM's machines. This is a good architecture for cloud storage, but it introduces 2 hops of network for the first time. Beforehand, only 1 hop of network is needed. Now look at the original kernel TCP. Data transfer using kernel TCP involves interrupt, context switch, lock, and multiple memory copies, which results in 100 millisecond latency. That's far more than SSD speed. It has become a bottleneck. We call the compute-to-storage hop as front-end network and the network inside the storage cluster as the back-end network. Remote Direct Memory Access, also known as RDMA, is a famous kernel bypass network solution in modern data centers. The transport protocol is very simple and is totally implemented in the RDMA-enabled NIC. When a packet arrives, it is directly transferred to application's memory through the DMA channel, saving at least 2 memory copies and user-to-kernel context switches. With RDMA, we can achieve 2 milliseconds of one-way latency. That sounds pretty good, right? So can we use RDMA for both front-end network and back-end network? Let's take a look at the differences between them. In terms of scalability, the front-end network usually crosses clusters and the number of connections can be over 100,000. However, to reduce the failure domain, the storage cluster is usually small in size and only intra-communications exist in backend network. For interoperability, front-end network needs to connect different clusters with different network cards, while for backend network, it is consistent in cluster configurations. There are 2 limits of RDMA. Firstly, RDMA's performance will drop a lot with over 10,000 connections. That's because it has little SRAM in its NIC, and more active connections lead to more frequent data exchange between host memory and the NIC RAM. Secondly, it is better to use RDMA for intra-cluster communications. Otherwise, the whole data center may encounter bandwidth decrease when any RDMA component fails. That's called a PFC storm. As a result, we choose to use RDMA for backend network to obtain the best performance, but for front-end network, RDMA is not very feasible. Data Plane Development Kit, also known as DPDK, is another kernel bypass solution. After configuring some rules on the NIC using DPDK flow director mechanism, the packets meeting the rules will be transferred to the user space memory by passing the whole stack of the kernel TCP. At that time, there were some alternatives such as fstack mTCP, which are both based on DPDK. However, the performance of these 2 solutions cannot meet our requirements, so we developed our own. Our user space TCP implementation is called Luna. As shown, when a data plane TCP packet arrives at the NIC, it is directed to Luna's specific hardware queues if its source port is within a predefined range. Then it goes through the DPDK layer, the Luna stack, the RPC layer, and finally reaches the storage service. To get the best latency for data I/O flows, we use busy polling, sharing nothing, top-down zero copy, getting rid of context switch, cache miss, intra-call locks. We know CPU is very precious, so we do our best to leverage hardware for stateless offloads like TSO and checksum. Finally, in Gen 2, the cloud storage architecture looks like this. We use Luna for front-end network and RDMA for the back-end network. Okay, let's move on to the second evolution from Gen 2 to Gen 3. The network evolution of this time is mainly driven by the appearance of bare metal. Beforehand, storage agent co-hosted with users' VMs, sharing the same CPU and memory, with users' applications running in the VM. This led to possible performance and security problems and inhibited storage agents' evolution since compute nodes are of different types. Ali Cloud's own bare metal infrastructure is called CIPU. To reduce power consumption and cost, it has only a few CPU cores and small amount of PCIe bandwidth. On the other hand, network failure and jitters are quite common, which can be disasters to storage. And the original Luna is implemented in software, causing a lot of CPU consumption, and the TCP protocol is hard to recover fast during the network failure, so it cannot meet the needs. Finally, we developed a new UDP-based transport protocol called SOLA. Before designing SOLA, we set 4 principles. First, reliability over performance over scalability. It needs to deal with common network failures, so reliability is the highest priority. Second, it should be hardware-oriented and can be implemented and largely deployed in software. Third, we can leverage modern switch functionalities like in-band network telemetry, but the protocol can work well without it. Fourth, it needs custom optimization for cloud storage, although not limited to this single scenario. Let's talk about SOLA's failure recovery first. Ali Cloud Data Center is a dual-homed factory structure. There are usually 5 layers of switches and around 50,000 different network paths between a compute node to a storage node. However, a traditional TCP flow only retries in a single path during congestion and network failures, which wastes plenty of time. For SOLA, one connection consists of 4 subflows with different fault tuples. When the application needs to send some data, the scheduler refers to the subflow table for their states and assigns one subflow to do the real data transfer. Any network failure or congestion leads to a rapid subflow exchange, so the overall connection is very robust. CIPU is Arli's own bare metal infrastructure. For Gen 2, cloud storage data generated from VM goes through the storage agent in CIPU and the entire Luna stack and enters the network through the NIC. CPU and the integrated PCIe on CIPU becomes a bottleneck for higher throughput in the near future. But for Gen 3, the exact 4 kilobytes raw data and its meta info is contained in one SOLA packet. When a SOLA packet arrives, the LPGA in CIPU can read this packet itself and direct it to the target memory address in the host. Only the meta info of the packet is transferred to the CPU of the CIPU, which largely frees up the CPU and the PCIe of the CIPU. And the last section is evaluation and lessons. With the 2 evolutions, the 2-hop network's average latency is decreased greatly. Let's take 95 percentile read latency for example. Luna in Gen 2 reduces the front-end network latency by 80%, and SOLA in Gen 3 reduces the storage agent latency by 40% by releasing the burden of CIPU. And from the right diagram, we can see that with SOLA, we can break through the PCI throughput bottleneck on the CIPU and achieve more throughput with increasing calls. At last, I'm gonna share some lessons learned from our large-scale deployment in production. First, algorithm is easy, but engineering is hard. Because the data center network topology is simple and relatively fixed, in order to achieve the ultimate performance, the TCP protocol stack can be tailored to a certain extent. For example, we only keep the simple neuronal algorithm and get rid of the MTU discovery mechanism of the standard TCP. The core algorithms of Luna or SOLA are less than 10,000 lines, but it takes us around 4 years to deploy them to production in large scale and verify their scalability. We need to test a lot of scenarios and gradually release them in grayscale. That's because production environments are very complex, with different network cards, different switches, and different behaviors of users' data flows. For example, we found kernel TCP and user space TCP like Luna compete with each other and cause performance degradation if we configure dozens of roles to the NIC via the DPDK flow director. It is not that hard to develop a new user space network stack, but deploying them in hundreds and thousands of machines is another story. Second, network's reliability is important. Network jitters and failures are quite common. For example, the whole production network experiences over 1 million times of network jitters in a month. We cannot fully rely on the upper applications to do failover whenever any network components fails, because upper applications have little knowledge of what really happened beneath, and it's really heavy for them to do that. That's one of the starting point of developing Solar. Third, the growth rate of network card and SSD bandwidth far exceeds that of CPU and memory bandwidth, with a throughput of several gigabytes. A hardware offloading solution should be considered. That's why Solar is hardware-oriented from the very beginning. However, hardware-oriented protocols are quite different from software-oriented ones. For example, the bitmap of the whole connection sliding window is quite hardware-friendly, but it's not the same for software. On the other hand, per-packet ACK is very friendly to hardware and congestion control, but it will seriously increase the burden of software. So I would recommend, if a protocol should be implemented in software, it should include aggregated ACK and piggybacked ACK. That's all for the sharing. Thanks for listening.